Welcome back. In this video, you will learn how to use the disk method to calculate the volume of solids of revolution. Let's get to it. Alright, so another application of definite integrals is the ability to find the volume of three-dimensional solids. In this specific video, we're going to be looking at solids that have cross-sections that are circles. And so if you take a look at this graph here, we have a function f of x and a shaded region beneath that function from a to b, where a and b are values of x along the x-axis. If we were to take that shaded region and revolve it around the x-axis, it would form a three-dimensional solid that has circular cross-sections. And so if we were to take a look at a small part of this region, let's say we look at this smaller rectangular region of this whole region, and we were to revolve just that rectangle around the x-axis, note that it would form the shape of a disk. Right, we would have this circular shape that we could call a disk. And this disk has a radius that is equal to the distance from the function to the x-axis. And so we would say that this distance here is the radius r of that disk. Now we could continue to draw more and more disks for the rest of this region. Right, we could choose another small rectangular region here or another one right here. And if we were to revolve those regions around the x-axis, we would form more disks that also have a radius that is the distance from the function to the x-axis. And so we could continue to draw more and more of these thin disks to make up this entire three-dimensional solid that would be formed by revolving this region around the x-axis. And so if we want to calculate the volume of that three-dimensional solid, or that solid of revolution, we just have to add up the volume of all these small disks that would make up that solid. And so if we take a closer look at this disk right here, I'm going to draw it upright. If you notice, a disk is essentially the same thing as a short cylinder, right? This would be a cylinder that's just very short. And we know that the volume of a cylinder is equal to the cross-sectional area times the height of the cylinder. And so in this case, this would be the height of the cylinder, and the cross-section of the cylinder is a circle, and so that area will be the area of a circle. And the area of a circle is pi r squared, and so the volume of a cylinder is equal to pi r squared times the height. And so this would be the radius of this cylinder. And note that that radius is still the distance from the function to the x-axis, this radius right here. And that remains true for all the other small disks that would lie between the points A and B. And then additionally, the height of the disk would be the thickness that you see right here. And so this right here would be the height. And so if we want to find the volume of the solid formed by revolving this region around the x-axis, we need to add up the volume of an infinite number of thin disks from A to B. And so this is where a definite integral comes into play. The height or the thickness of the disks could be viewed as dx, or a small change in the value of x, and we would multiply dx, or the height, by the cross-sectional area for that solid of revolution. So the volume is equal to the definite integral from a to b of the cross-sectional area in terms of x times the height dx. Right, this is just the volume of a single disk, but we're adding up an infinite number of them with this definite integral from a to b. And remember, we said that the cross-sectional area of one of these disks is just equal to the area of a circle, which is pi r squared. And so this cross-sectional area would be equal to pi r squared, where we can view the radius as a function of x, right? The distance from the function to the x-axis is the radius, and so we can just view this function as the radius for all of our disks, right? No matter where we are along this function, this represents the radius of a disk that could be drawn at that particular point in the region. And so we could rewrite the cross-sectional area to be pi times the radius function squared and then multiplied by the height dx. And this right here, this formula, is what we call the disk method, because this will calculate the volume of a solid of revolution using an infinite number of disks. Okay, so this is the formula for the disk method when we are looking to calculate the volume of a solid of revolution when the region is revolved around the x-axis, but we could also come up with a similar formula for when we want to revolve a region around the y-axis. And so let's take a quick look at that next. Okay, so if we want to revolve a region around the y-axis, note that we have the same function here, but now it's in terms of y, right? We have f of y, and we have our shaded region from c to d, which are two values of y, and we're going to revolve this region around the y-axis. And so you can imagine that this would also form disks that we could calculate the volume of and add together to get the total volume of the solid of revolution that would be created by revolving that region around the y-axis. And so we could have another disk down here, and so on, right? We could continue to draw more and more disks that would represent the volume of that solid of revolution. And so, in this case, the radius of these disks would be the distance from the y-axis to that function f of y. And so if that's the radius, then that means that the volume of this solid of revolution will be equal to the definite integral from c to d of the cross-sectional area, but in this case we know that that cross-sectional area is the area of a circle, which we know to be pi r squared, and so I'll rewrite that to be pi times the radius squared, which in this case the radius will be a function of y, because the distance from the y-axis to this function in terms of y is the radius, and so we can view this function as the radius function in terms of y, and so we'll multiply pi by that radius function in terms of y squared, because the area of a circle is pi r squared, and then we'll multiply by the height of these disks. And so the height in this case would be right here, and we could rewrite that as dy instead of dx, because that represents a small change in the y values instead of the x values, and that is going to be the height of those disks. And so we'll multiply by dy. Okay, so if you want to calculate the volume of a solid of revolution where a region is revolved around the y-axis, then we can use this version of the disk method to do so. The difference between the two formulas is that your bounds of integration will be values of y instead of values of x, and your radius function will be in terms of y instead of in terms of x, and we will be integrating with respect to y instead of with respect to x. Okay, and so in summary, here are the two formulas you need to know for the disk method. If you're going to calculate the volume of a solid of revolution that is being revolved around the x-axis, then you want to use this formula where the volume is equal to pi times the definite integral from a to b of the radius function in terms of x squared times dx. And if you want to calculate the volume of a solid of revolution that is revolved around the y-axis, then you want to use this formula, which is essentially the same formula, except everything is going to be in terms of y. Okay, so now that we know the formulas for the disk method, let's take a look at some example problems. Alright, so here's our first example. We want to find the volume of the solid that results from revolving the region enclosed by y equals the square root of 2x, y equals 0, x equals 0, and x equals 2 around the x-axis. Okay, so the first thing that you want to do for a problem like this is to graph everything that you've been given. And so if we draw the y-axis here, and then I'll draw the x-axis, and then I'll label them. So here's the y, and here's the x. And then what we'll do is graph each of these equations. So I'm going to graph y equals the square root of 2x. We know that the square root of x function is shaped like this, and that 2 multiplied by that x inside the square root is just going to compress the shape of that function a little bit, but we're not trying to draw a perfect graph here. We just want the general shape that we're looking at, and so this is our function y equals the square root of 2x. And then the line y equals 0 is just the x-axis, right? That's where y is equal to 0. X equals 0 is just the y-axis, right? That's where x is equal to 0. And then we have our final line, x equals 2. And so if we say that x equals 2 is about right here, then we can draw our line x equals 2, and now we can see what our enclosed region is going to be, right? So between all of these lines, we have this region right in here. This region that I'm shading in is the region that we are going to be revolving around the x-axis in order to get a solid of revolution, right? We're told that the solid results from revolving the region enclosed by these equations around the x-axis. And so I'm going to signify that by drawing an arrow around the x-axis. Okay, and so since we're going to be revolving this region around the x-axis, that means that we will be working in terms of x, and so we are going to be using the following formula for the disk method. We'll have that the volume is equal to pi times the integral from a to b of the radius function in terms of x squared times dx. Now all we have to do to set up this definite integral is decide what two values of x our region lies between and what the radius would be for the disks that would be formed when revolving this region around the x-axis. And so let's start with the bounds of integration. We will have that the volume is equal to pi times the definite integral from the lower bound to the upper bound. And if we look at our region, this region lies between the x values of 0 and 2. And so our bounds will be from 0 to 2. Okay? And then we want to figure out what our radius is going to be for this solid. And remember, since we are revolving around the x-axis, the radius is going to be equal to the distance from the x-axis to the top of this region. And in this case, the top of this region is entirely this function, the square root of 2x, right? So this distance right here is r of x, and that is going to be this curve, and so our radius is the square root of 2x. That will be our radius function, and we will square it and then multiply by dx. All right, and so now all we have to do to calculate the volume of the solid of revolution formed by this region revolved around the x-axis is to solve this definite integral. And so if we simplify it a little bit by squaring this square root function, we will have that the volume is equal to pi times the integral from 0 to 2 of the square root of 2x squared. Now when you square a square root function, it actually just cancels it out, and so we're just going to be left with 2x. And so we will have 2x times dx. And now what we're left with is a pretty simple definite integral that we should know how to solve. And so if we clean up our work, the volume will be equal to pi times the integral of 2x. Now to integrate 2x, we're going to need to use the power rule of integration. So we'll add 1 to the exponent and then divide by that new exponent. And so we'll have 2x squared divided by 2, and that will be evaluated from 0 to 2. All right, and so then these 2's will cancel out, and so this will actually be equal to pi times x squared evaluated from 0 to 2. And now we just plug 2 into this expression and then subtract, plugging in 0. And so we'll have that this is equal to pi times 2 squared minus 0 squared. And of course, 0 squared is 0, and 2 squared is 4, and so this is equal to pi times 4, which is equal to 4 pi. And so 4 pi is the volume of the solid of revolution that is formed when you revolve this region around the x-axis. All right, so now that you've seen an example where we calculate the volume of a solid of revolution formed by revolving a region around the x-axis, let's look at calculating the volume when we have a region revolved around the y-axis. Okay, so here we want to find the volume of the solid that results from revolving the region enclosed by y equals 3 times the square root of x equals 0, and y equals 6 around the y-axis. Okay, and so the first thing that you want to do is to graph everything that you've been given. And so let's draw a y-axis here, and then I'll draw the x-axis, and I'm going to label them. So we'll have y and x. And now let's graph each of our functions. And so here we have y equals 3 times the square root of x. It's going to be a very similar graph to what we had in the previous example. We know that the square root function is shaped like this. It might be a little bit compressed once again because it's being multiplied by 3. But either way, we're not looking to draw a perfect graph here. We're just trying to get an idea of the shape that we're working with. And so this is y equals 3 times the square root of x. And then x equals 0 is just the y-axis. And so we don't need to worry about drawing that line. And then for y equals 6, let's say that y equals 6 is right about here. So I'll label that as 6. And then we can draw our line to represent y equals 6. All right, so this is y equals 6. Okay, so now we can see that between the y-axis, y equals 6, and 3 times the square root of x, that this is the enclosed region that we are going to revolve around the y-axis to form a solid of revolution. And so I'll shade in this region here, and then I'm also going to label which axis we are revolving around. In this case, we are revolving around the y-axis, and so I will draw a little arrow around the y-axis. That way we don't forget which axis we are revolving around. Okay, and so since we're revolving around the y-axis, that means that we're going to be working in terms of y, and so we are going to want to use the following formula for the disk method. We will have that the volume is equal to pi times the integral from c to d, where those are values of y, of the radius function in terms of y squared times dy, right? So everything should be in terms of y. Our bounds need to be in terms of y, our radius needs to be in terms of y, and we're going to integrate in terms of y. All right, and so let's determine what our bounds of integration will be. We'll set up our definite integral here. The volume will be equal to pi times the integral from a lower bound to an upper bound in terms of y, and it looks like our shaded region here is located between the y values of 0 and 6. And so our lower bound will be 0 and our upper bound will be 6. And now we need to determine what our radius will be in terms of y. And so if we look at our shaded region, remember we are revolving around the y-axis, which means that the radius will be equal to the distance from the y-axis to the top of our region, or in this case, since we're working in terms of y, the right side of the region. And in this case, no matter where we go along our region, the distance from the y-axis will be this function right here, y equals 3 times the square root of x, right? This right here is the radius in terms of y. However, note that this equation right now is expressed in terms of x. So do not write 3 times the square root of x squared times dy, right? That would be incorrect. It needs to be in terms of y, and so let's solve for x in this equation, and that will tell us what this curve is in terms of y. And so we're working with y is equal to 3 times the square root of x. If we divide both sides by 3, we will have y divided by 3 is equal to the square root of x. And then to solve for x, we just have to square both sides to cancel out that square root. And that will give us that x is equal to y squared divided by 3 squared, which is 9. And so this is the radius for the cross sections of the solid of revolution that will be formed when this region is revolved around the y-axis, right? The distance from the y-axis to the top of our region, or in this case, the right side of the region, is this function, which we now have expressed in terms of y. And so if we go back to our definite integral here, we will be integrating y squared divided by 9, and we will square that and then multiply by dy. Okay, and so now we have set up a definite integral that will calculate the volume of the solid of revolution that is formed by revolving this region around the y-axis. And so if we simplify this a little bit, we'll have that the volume is equal to pi times the definite integral from 0 to 6 of y to the 4th power divided by 9 squared, which is 81, times dy. And so if we clean up our work here, we can pull this 1 divided by 81 to the outside of the integral and have that the volume is equal to pi divided by 81 times the definite integral from 0 to 6 of y to the 4th power times dy. And now we just have to solve this definite integral, which shouldn't be too hard for us to do if we use the power rule of integration. And so this will be equal to pi divided by 81 times y to the 5th power divided by 5 evaluated from 0 to 6. Right? If we use the power rule of integration, we add 1 to the exponent to get y to the 5th power, and then we divide by that new exponent of 5. Okay? And so now we will plug 6 into this expression and subtract 0 plugged into this expression. And so this will be equal to pi divided by 81 times 6 to the 5th power divided by 5 minus 0 to the 5th power divided by 5. And so if we clean up our work once again, we can simplify further, and this will be equal to pi divided by 81 times 6 to the 5th power, which if you plug into your calculator is 7,776, and that will still be divided by 5. And then we will be subtracting 0 to the 5th power divided by 5, but that's just equal to 0, right? 0 to the 5th power is 0, divided by 5 is still 0. So we would be subtracting 0, but we don't really need to write that, and so I'll close that. And then we can simplify by multiplying pi divided by 81 by this fraction. And if you divide 7,776 by 81, that will give you 96. And so this will be equal to pi times 96 divided by 5. And so our final answer is that the volume is equal to 96 pi divided by 5. And that will be the volume of the solid of revolution formed by revolving this shaded region around the y-axis. All right, and so with that, that is all I had for this video on the disk method. If you want to see some more complicated examples, feel free to check out my examples video that I'll have linked at the end of this video as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.